All right, let's take a look at what happens when we transform the graph of y equals sine x. So remember, in a previous lesson, we looked at y equals sine x or sine t. We'll use x this time, it doesn't really matter. So this would be our x-axis, our y-axis. And we kind of drew the graph, and we showed that that graph starts at 0, 0. It reaches its maximum value of 1 at pi over 2. It comes back through the axis at pi, reaches as a -1 value at 3 pi over 2, and it ends up back at 2 pi, and then continues that pattern. And I can kind of continue the pattern backwards if I want, like so. And let's now take a look at what happens. And well, just to recap, remember we said that this function has amplitude 1 and period 2 pi. All right. If I put a 2 in front of the function now, and let's look at the graph of y equals 2 sine x. Remember, the 2 in front of the function here has the effect of a vertical stretch by a factor of 2. And so my peaks are going to become twice as high, my valleys are going to become twice as low, and my zeros are going to stay the same because 2 times 0 is still 0. All right, so you know, the graph of y equals 2x, 2 sine x, will pass through 0, 0, but instead of reaching a height of 1, it will now reach a height of 2, like so. It'll pass through the point pi 0, and out here at 3 pi over 2, instead of reaching a depth of -1, it'll reach a depth of -2. So when I look at the graph of y equals 2 sine x, I see something like this. Pretend like I can sketch decently. And now our amplitude of this is increased to 2, and our period remains the same because the graph still repeats itself. The pattern repeats itself every 2 pi radians. All right, you can also imagine that if I had placed, a smaller number, a number smaller than 1 in front of my expression here. So if, for example, my function is y equals 1/2 sine x, all right, half of 0 is still 0. So the zeros of 1/2 sine x will again still be at, these are actually multiples of pi. However, the height of my graph, the maximum value now will be 1/2 rather than 1. So I'll see that my peaks are lower, my valleys aren't quite as low, and this kind of has the effect of flattening out the graph a little bit. And now I have an amplitude of 1/2, and again our period is the same. So the effect that we've observed here is that when we take a function like sine x and place a constant in front of it, we know that this constant will change the amplitude of the graph. So our new graph will have an amplitude of the absolute value of a. And I didn't do an example where a was negative, where we actually reflect the graph over the x-axis. But if that's the case, amplitudes are positive no matter, if the coefficient in front here is negative or positive. All right. And if the absolute value of a is greater than 1, we know that we're going to vertically stretch the graph. And if the absolute value of a is between 0 and 1, we're vertically compressing the graph.